All right, we are live. Hello, everyone. I see that we've got some people watching us online already. Welcome to those of you who are viewing this live, and welcome to those of you who will be looking at us in the future. Here we are time traveling on Sidewalk Science. This Sidewalk Science program is brought to you by a local chapter of the American Humanist Association. We are the Prairie State Humanists, and the American Humanist Association has provided some practical and financial support to help us with this program as well. Abby Hafer, who is one of our regular panelists, is also on the board of the American Humanist Association. And one of the things that we try to do on this program, and I suspect I would like to see us do even more in the future, is dealing with the intersection between humanism and science. When it comes to dealing with issues where science disagrees with religious traditions and religious fables and whatnot, as well as anything that's supposedly miraculous or supernatural. As secular humanists and scientific skeptics, all of us believe that the best way to understand and cope with what's real in the universe is through science. And so we have this Sidewalk Science program where we talk about some news stories related to science, as well as having a deep dive topic for more than half of our program. Today's deep dive topic is going to be provided by Dr. John Doty, who has designed a lot of spacecraft instruments that have provided us with quite literally a lot of insights into the way the universe works. And I'll let him talk about that, and especially the idea of spectroscopy, which is kind of a follow-up to what Dr. Reed talked about last week with her discussion of light and how we learn about the universe from light.
We could do 100 of these on spectroscopy. It's so deep.
Yeah, we've been, what is it? We've been at this for ever since, Joanne, who was it that you said was the first person that sort of discovered the spectral lines of elements and whatnot?
I think it was old Ike Newton, wasn't it?
Well, I'm not sure he's...
No, actually, that was Fraunhofer.
Fraunhofer.
The lines.
Right. So ever since Fraunhofer, we've been working to pick apart all of the intricacies of the way light works and the way it can convey to us information about the universe, whether it's chemical under scrutiny in a lab on Earth or a distant star or a galaxy, etc.
They're both emission and absorption that we can work with. So it's
Right.
fun.
So those of you who have joined us on YouTube, feel free. You should see a little chat box beside the video feed, and you can use that chat box to ask questions or make comments as we go through our program today. Please give us a thumbs up or thumbs down if you happen not to like us, but subscribe, leave comments, interact with us. We're not doing this for our own edification, although we learn a lot from each other. We're doing this for you. So thank you for joining us live, and thank you for those that will tune in later. So let's get started with some science news. I've picked out two stories that I want to talk about today, and then we'll have time for others to bring up some news stories as well. The first is some possible discovery. I'm looking off to the side. I have two monitors here. So possible discovery of 125 million year old dinosaur DNA. I don't know if the rest of the panelists have seen this story or not. But in China, there is a feathered dinosaur called, I'm probably going to butcher this name, Caudipteryx. That's a Caudipteryx. Caudipteryx. A small they have, some scientists claim that they have extracted bits of DNA from, I believe it's thigh bone. I'm not going to reread the whole story here live. But there are other scientists, oh, by the way, did I say 125 million years old? There are other scientists who say that this is hard to believe because theoretical and practical experiments have led many others to conclude that the greatest length of time that DNA could survive without breaking apart and becoming unrecognizable, it's a very long, complicated molecule and, in a sense, pretty fragile. Other scientists say that the absolute longest that you could expect a piece of DNA to survive would be about 1.5 million years. So prior to this, the record was about 1.2 million years for some DNA extracted from a mammoth in, I believe, Siberia. So this, increases that by a huge amount. And, by a factor of about, 100? And so there are scientists that are pretty skeptical about it. But if it turns out to be true, then that could be very interesting to actually have some DNA in hand. Some of the scientists that are skeptical say that it's probably mineralized, that the individual DNA strands and the chromatins might have been replaced by minerals. I don't know what minerals they would be, but maybe quartzite or other sorts of minerals that can be transported with water. So interesting, dinosaur DNA. One of the things I wanted to point out about the intersection of science and humanism about this is just another piece of evidence that the world is not, in fact, only 6,000 years old. Just in case there was any lingering doubt about that, finding this dinosaur from 125 million years ago. There's bountiful evidence that life has existed on this planet for billions of years, and what we would call complex life, for about 500 million. So, interesting science story. Do any of you have thoughts about this story, or have you seen it and have your own comments?
I'll line up with the skeptics. It's nice. Could there be pieces of it? Yeah, but the entire full length of the chromosome? No.
I think they were just saying bits of DNA. I'm not sure they were talking about full chromosomes.
Find bits, but what do we mean by a bit? A protein? 2 proteins?
Nucleotides, right? Yeah.
I'm really hesitant on this.
Yeah, I think they did a chemical test. The chromatin within the cells of living organisms on Earth is made of highly packed DNA molecules, and there's a dye that they can inject into biological material that specifically fluoresces with regard to interacting with chromatin, and they saw this fluorescence.
Where did you get this from, Scott?
I'm sorry, what?
Where was the article?
The article is on Science SciTech Daily, SCITEACH Daily. That's the one I'm reading.
Oh, all right. I haven't seen it, so yeah, I'll look it up.
Abby or John, do you have thoughts?
I'm just a silly little physicist. I haven't.
I know that you have thoughts. I've seen them happening.
I've seen thoughts.
All right.
Ooh, I have a thing. Right back.
Okay. The second news story that I wanted to highlight this week was a recent announcement that the biblical story of Sodom and Gomorrah might have some, albeit fairly tenuous, connection to a real event. Some archaeologists have discovered that there was a city in the Middle East called alHaman. I'm not sure if that's what it was called 3,600 years ago, but that's the modern name of the archaeological site, alHaman. And by looking at some debris in the archaeological ruins, as well as evidence of extremely high temperature layer of ash and debris. Scientists have concluded that, again, 3,600 years ago, about 8,000 residents in that town were annihilated by a fireball, an asteroid that crashed near their city, and as powerful as a large nuclear weapon. The shock wave from this event reached so far that it also is implicated in one of the many instances in which the city of Jericho was destroyed as well. And Jericho's walls came down, and a lot of people in Jericho were killed by this fireball as well. And the Tel alHaman village or city of about 8,000 people was on the shores of the Dead Sea, and that area is very salty and whatnot. And the articles say that after that collision event, that land became non-arable, so they could not grow crops on it for hundreds of years. So again, that's all consistent with some elements of the biblical story about, the land being salted and ruined and the city being destroyed, and it also potentially ties into the myth about trumpets bringing down the walls of Jericho. And we haven't talked in this forum yet about ideas of the global flood, which briefly can be correlated with perhaps tales passed down through generations from the end of the last ice age, when glaciers were melting and glacial lakes were overflowing their banks and whatnot. But in any case, the larger point I'd like to make is that some of these ancient tales that have been passed through time and have had sort of ornamentation of moral fables, right, about Sodom and Gomorrah being cities of sinful people, that some of those bits of moral ornamentation are tacked on to explain why a god would possibly cause floods and meteorites and the destruction of cities and city walls and whatnot. When you don't have science to help you understand the universe, anything extraordinary that you witness seems like magic, seems miraculous, and makes you plausibly think about the wrath of a god. So the science behind some of these stories ends up being at least, if not, I would say, much more fascinating than just some angry deity.
Well, and you can easily see how, if a fireball comes out and destroys a city, that's the kind of thing where, that would tend to make you think that, what did that city do wrong to deserve that kind of thing? I mean, that pretty much deserves having a story made out of it. If you're an ancient people and these kinds of things don't happen very often, ascribing a fireball out of the sky to a deity seems like that's not a big stretch.
Yeah.
No.
My favorite theologian, Karen Armstrong, in her book, A History of God, complained that the ancients took everything that they saw that they didn't understand and called it God.
Yeah. Still do today.
Yeah. Well,
Yeah.
some of us prefer to try to understand the stuff.
Right. Well, and to your comment, Joanne, about it still happening today, I would amplify that a bit and say that for many things that people attribute to the supernatural to this day, there is a perfectly and incredibly plausible natural explanation, like evolution, right? The theory of evolution by natural selection is an incredibly beautiful and persuasive idea, and a well-tested discovery about the way nature works. But something slightly less
theory in every regard, in that it not only predicts, but it also explains. It allows us to experiment, and we can actually go back into the entire process and disrupt it, change it, modify it. We do that all the time. In fact,
most recently, we did it with a virus. We actually looked at the virus and said, what is your composition? And we're going to go in there and we're going to find another doohickey that interferes with you. So it's a wonderful explanation, it's a perfect theory.
Right. Well, and we're probably all old enough to remember when AIDS was ascribed to the wrath of God. Then we found HIV.
Right.
And so, another perfectly good wrath of God bites the dust. The wrath of God doesn't last us long these days because we usually figure out what really happened. But this always brings up what's called the God of the gaps argument, which is basically any time that something is not explained, people who really want to insist upon the supernatural will say, you can't explain this thing, therefore God must be doing that. And then, of course, when science winds up explaining that, they say, well, there's this other smaller thing that still hasn't been explained, and God winds up being stuffed into these rather sad little crannies, which is kind of a sad location for somebody who is supposed to have, invented the universe and done other very big and important things. But the God of the gaps argument is something that comes up pretty routinely.
Yeah, it's a desperate explanation for things that we may not have other explanations for. And then, right, except today, many of the things that...
But to get back to the original article,
the thing which I think convinced me of their evidence was the shocked quartz.
Yeah.
Shocked quartz only occurs with extreme violence. The first time that we really knew about it was, of course, at Alamogordo, when we began looking at the what was left after the Trinity test, and we looked at the silicon dioxide, and we saw these beautiful crystals that had been cracked in a precise manner, that they've been hit with such a huge amount of energy that the crystal structure was beautifully cracked, and we called it shocked quartz. Later on, we discovered that in instances where there has been an impact on our planet, something from somewhere else came in and said, I'm going to hit you really hard. That we found the shock quartz again and again and again. And this is one of those signs that, yes, and something has come from beyond our atmosphere and has hit us really hard. And so this is the key as far as I'm concerned. If you find the shock quartz, you can go, aha, got it. If you don't find the shock quartz, you go, yeah, maybe not.
Right. Yeah, I don't know, for example, if the Tunguska event is associated with shocked quartz. That seemed to be more of an airburst of something that was more volatile, like a comet, I think. But I don't know for certain about the shocked quartz. Or
in the Megiddo thing, I'm sorry,
Sodom.
yeah, Sodom.
Yeah. All right.
Good, got it.
Anybody else have any science news stories that they were intrigued by in the past week or two?
I got an article. I'm going to hold it up here so everyone can see it. This is the latest Science News magazine, and there is an entire section, a very large section, on the human story. I do recommend it. It's a short article. We have a thunderstorm going on out here, so welcome to either spring or fall. But it's a wonderful story, wonderfully comprehensive, and does tell a pretty good narrative of where we started from all the way through to, just a few thousand years ago, when this particular species sort of took everything over.
So I recommend it highly as, again, the human story in Science News.
Cool.
Excellent.
John or Abby? Yeah.
I was going to, if people want to discuss Joanne's article, I'd love to hear more, but I just want to queue up that I have kind of a fun article after that.
Yeah, nobody is chatting about it yet on YouTube, so go ahead, Abby.
Okay, so there's this fun article in the Atlantic from September 28th about sea slugs. And these are sea slugs that have chloroplasts. They can photosynthesize. One of my sort of favorite kinds of organisms are the ones that break the rules and sort of blur the lines of the categories that, of course, we have created. Biology never really cares about the rules that we make for it or the classifications that we create. But this is basically, there are not just one species, but a number of species of sea slugs that basically eat algae and then retain the chloroplasts. And this has been known to science for a while, but there's a wonderful article here about the fact that these sea slugs can more or less eat once in their lives, retain the chloroplasts, and then because sea slugs don't have sort of tremendous energetic needs, they don't warm their bodies and things like that. They can actually just they can eat once and then that's it if they need to. So it's a pretty cool article, and there's a whole lot about how do they keep those damn chloroplasts alive, because it turns out that's not easy. Chloroplasts secrete toxins and do some other things that aren't friendly. But it brings up two really fun topics, one of which is endosymbiosis, which is largely how we think we actually got eukaryotic cells, is by having had essentially ancient bacteria engulfing other ancient bacteria and living together as symbiotic organisms. It's pretty clear this is how chloroplasts got into eukaryotic cells, not into animal cells, but into plant cells. It's how mitochondria got into cells. Because mitochondria and chloroplasts both retain their own DNA and can reproduce separately from the cells that they're in, and otherwise act remarkably independent for something which is an organelle. And so here's this very nice article about chloroplasts and what it takes to keep these chloroplasts alive when the algae is stripped away and the sea slugs just keep the chloroplasts. So this is pretty wonderful. And of course, it totally messes with the whole categorization of autotroph versus heterotroph. And, who does photosynthesis and who doesn't.
Abby, could you explain those autotroph and heterotroph terms for our listeners?
Yeah, autotrophs are, as the word implies, self-feeding, auto meaning self, like automobiles are self-moving. Autotrophs are self-feeding. So these are your green plants because they don't need to eat anything else. They just orient themselves towards the sun and they do photosynthesis, and that's how they get food, basically the chemical energy that they need. They convert solar energy to chemical energy and then use that to grow. We animals, on the other hand, for instance, are heterotrophs, basically meaning we have to eat something else in order to keep going. But these sea slugs, despite being very much animals, nonetheless can photosynthesize. So it breaks down that category. And well, this just kind of brings up the whole subject of classification, which is always something that biologists can discuss at length. And sometimes people get rather cranky about it, and physicists are not immune to this. There are still arguments about whether Pluto ought to be a planet or not. But it's the kind of thing where people will continually tell you that which is true, which is that classification, that our various classifications and categories are all invented by us. Nature does not really care. Nature does whatever it's going to do. But I'm also going to say that although that is true, classification is nonetheless incredibly useful because it would be difficult to talk about anything really in science without classification. And to use just one example, evolution by natural selection. We were just discussing it a minute ago. Neither Darwin nor Wallace would have been able to discover evolution by natural selection if they hadn't looked at species distributions. To study species distributions, you have to be able to tell the difference between closely related species and where they are and all of this kind of thing. So classification is one of those things that I think the proper attitude is that you ought to love to hate it. It's a pain in the neck. We never get it quite right. We're constantly changing our classifications, but we really couldn't do science without it.
And a lot of classifications have fuzzy boundaries.
Oh, yeah. And we change them all the time. And we discover that some class really we ought to lump 2 or 3 classifications together into one. And then other people will argue that you ought to split them apart. There is famously in botany and almost any time that you do this kind of work, there will be arguments between splitters and lumpers, as they are known. Splitters being the ones who think that like everything ought to have its own separate category, and lumpers being the ones who say, oh, these ones are also similar. Let's just put them together in that. So as I said, these conversations go on and on and on. And sometimes they're fun and sometimes they're annoying. But as I said, the problem is we really can't live without them.
Yeah.
You mentioned that it was difficult for these creatures to maintain these chloroplasts. But isn't this something that we've always known, that it's not easy being green?
Very good.
Nicely put, Joanne. All right. Well, in the interest of time, John, do you have any quick science stories you want to tell us about, or shall we move right to your exposition about spectroscopy?
Let's go to spectroscopy.
All right.
All righty, let's see if I can get this to work.
So there.
Can you see my screen?
Yes.
All right. Well, spectroscopy to me is a very underappreciated part of physics and chemistry. It really is the thing that you turn to when you've got a puzzle and you can't figure out how to solve it. It's the magic wrench that unscrews the inscrutable. And Joanne started with Newton. I'm going to start with Fraunhofer because Newton didn't do very much for spectroscopy. He did a little bit, but Fraunhofer was really very important and where modern spectroscopy started. And part of it is that he was the first to really do diffraction grating spectroscopy. And the way a diffraction grating works, I'm going to talk quite a bit about gratings, is that if you have incoming waves and you run them through a slit, it's kind of like a breakwater in a harbor where the waves come in and they mostly get stopped by the opaque material here, but some of them get through this gap and then they spread out from the gap. And so you have outgoing waves going in a lot of directions. And that is the first thing that you have to put together to make a grating. Now we have a bunch of slits. Now this is a very busy diagram, and I'm going to explain this in another way in a second. But you have outgoing waves coming from all these different slits, and they tend to add up in certain directions. So if you look at these incoming waves, there's a wave that comes from the same direction as the incoming waves, is tangent, it kisses all these circles, and that means that it tends to add up. And so you get a wave that is duplicating the incoming wave going like this. We call this order 0. But here's another wave, and it touches the first wave from this slit, and the second wave from this slit, and the third wave from this slit, and the fourth wave from this slit, and the fifth wave from this slit, and it goes in this direction. And that's order one. When you chop this incoming wave up like this, it makes it possible for the outgoing waves to add up together in other directions, as well as the order zero, which goes in the same direction. And then we get order two from this diagram, where it touches this first wave from the first slit, and it touches the third wave from the second slit, and it touches the fifth wave from the third slit. So it touches every other wave like this, and it goes out like order two. And these directions depend on what the wavelength of these waves is. And now I'm going to try and explain it in another way. Okay. This is my little gizmo here. And basically what this is you can see here we have the incoming waves, and I've got a blue wave and a red wave, and they have different wavelengths. And it's straight on, the waves all line up. So this is order zero. They all come out like this. Now, if I move this over a bit, then the first thing that happens is that get all lined up. The blue waves line up. You can see that this wave lines up and this wave lines up. And so we've got blue waves going off in this direction as well. And now I move it over a little more. Now, the red waves line up. So the red waves are going off at a higher angle than the blue waves are. And so what we've done is we've separated the red from the blue. Exactly. And then we go a little farther, and we can even get to order, with this gadget, we can even get to order two in the blue waves, where like that, where they go even farther out. And this one can't quite reach order two of the red waves. So that's how a diffraction grating works. Fraunhofer was really the first to get much out of diffraction gratings. They had been invented by somebody, and there are disputes as to who, in the 18th century. But the technique was to get two very fine thread screws, and then string either extremely fine wires or hairs between the grooves in the screws. So you would get a grating made out of hair or wire, but you couldn't get it finer than you could groove a screw. And that's not very fine. And unfortunately, when you have a very coarse grating, the problem is that you get a lot of grating orders, and they all overlap. And so the spectra are really jumbled up. What Fraunhofer did was he made the first ruling engine. And I called spectroscopy a great underappreciated science. The ruling engine is a great underappreciated technology of science. A great underappreciated instrument. What you do is you get a little sharp pointed tool, and you put it on some sort of sliding stage so it can only move in one direction. And now you take a surface, and what Fraunhofer used for his first experiments was glass coated with gold. And you run the tool along the surface, and you make a groove through the gold. So you've cut through the gold, and you can get through to the glass. Now you use a screw, but it's over here, and you turn it just a tiny little bit. You don't turn it a whole way around. You just turn it maybe 1/100th of a rotation. And that moves the thing that you're ruling over a little bit. Now you run the tool over it again, and you make another little groove. And you can make an extremely fine set of grooves on a piece of glass. I believe Fraunhofer made 4,000 groove gratings. And if you ever see one of these things, they may you hold them up and they make rainbows. If you look at them with a microscope, you can see the grooves, but you can't see the grooves with your eyes. And that was a tremendous advance, because now you can make a grating spectroscope without all this confusion. And the other advantage of a grating, Fraunhofer also worked with prisms like Newton did. But the other advantage with a grating is, because you've made it with a screw and you can calibrate the screw very carefully, you know how many threads per inch it has, and you know how much you turned it. You know how close the grating grooves are. And how close the grating grooves are, I mean, this is it, here and here, determines what the angles are for different wavelengths. And so you measure the angle. You could use a little analog computer like this to figure out the wavelength of your light, or you can do the math if you like. You get the actual wavelength that you're working with quantitatively. You're not dependent on the quality of the glass. You know, everybody gets the same answers because you can use standard rules to figure out you can use meter sticks or whatever to figure out the pitch of your screw, and then you do protractors, and you figure out the angles, and everything is measurable and known, and you can relate that to the wavelength of the light you're working with. And that was a tremendous advance, because it made it possible to compare different spectra. Okay, back to sharing. Why do we call them lines? Why are they lines in the Fraunhofer spectrum? Well, Fraunhofer didn't just invent the ruling engine. He invented the modern spectroscope. And his spectroscopes were basically telescopes with either a prism or a grating inserted in the optical path in a strategic location to move the images around. And so you look through a he looked through these things. He didn't have photography. And you look through the telescope and you see an image of whatever you're trying to analyze. Well, and the images, the red and the green and the blue are spread out, but the image is spread out. And so what he did was he added a slit to the system, and he focused his telescope on the slit, so that you get, instead of the image of the object that's making the light, you get an image of the slit. And now you shine the light on the slit, and you get to make very narrow features for the various spectral features in your spectrum. And you look at them and they show up as lines. We still call them lines even when we're not using this kind of spectroscope. Here's a completely different kind of spectroscope. This is an X-ray spectrum of the Perseus cluster of galaxies, and we call all these peaks lines. They don't look like lines, but the terminology has stuck. And that's from Fraunhofer. We're very conservative about some things in science. And this is a very different kind of spectroscope, and I'll get back to this kind in a bit, but this does not use a grating or a prism. A lot of scientists have worked on spectroscopy, and you've heard their names. Foucault, of Foucault pendulum fame, was the one who figured out the relationship between emission lines and absorption lines, where If you have a hot, bright source of light behind a relatively cool gas, you get absorption lines like Fraunhofer did. When you have a dark background to a hot gas, you get emission lines. He figured this all out. He even figured out the temperature part of it, which astounds me, because the statistical mechanics part of physics that you kind of need to understand that hadn't been invented yet, but he kind of figured it out. And now you know something about the sun. You know that there's a hot layer that's making a lot of light and a cooler layer that's making the Fraunhofer absorption lines. You've dipped a thermometer into the sun using spectroscopy. But Foucault isn't so famous for this. He's famous for his pendulum. Bunsen, he's famous for this silly little, gas burner. He did an enormous amount of stuff other than that, and especially he worked on spectroscopy. One of the things that, in the middle to late 19th century, spectroscopy really started to take off with element discoveries. Bunsen and Kirchhoff started doing their flame spectra with Bunsen's burner, and they characterized flame spectra of a bunch of elements. And then they had a sample of some salts, and they found some new spectral lines in them. Oh, well, we've got a new element or two. So then they proceeded with the hint that there's another element there. They're skilled chemists. They know how to purify things. They found methods to purify new elements out of this mixture of salts, and they called them cesium and rubidium. Brand new elements hadn't been known before spectroscopy. At about the same time, Lockyer and a number of other people, I credit Lockyer because he really named the stuff. He was really brave enough to say, this line in the solar spectrum doesn't match anything we know about. And so it must be a new element. And he called it helium. And eventually, a couple decades later, helium was isolated as a gas, and it had the spectrum it had in the sun. And so, yeah, it's a real gas. So,
John,
that's great. Well, now let's look at other spectra. Well, a fellow named Huggins looked at the Cat's Eye Nebula, and he found a couple of lines that didn't match anything. And he figured, okay, it worked for these guys, it better work for me. So he claimed the discovery of nebulium. We'll get back to why you've probably never heard of nebulium in a little bit. The next big thing was that spectroscopy was behind the invention of quantum mechanics. Because by the end of the 19th century, electromagnetism was well enough understood, statistical mechanics was well enough understood, that you could ask the question, what does electromagnetic radiation look like when it's in thermal equilibrium? And the theory is this black line. Oops, didn't mean to select it. The theory is this black line. But you can go and measure it. The usual way is you make an oven and you put you make dark walls to the oven, and you heat it to a uniform temperature, and you put a little hole in it. And now what you've got is you've got a lot of radiation in there that, because the oven is at a uniform temperature, the radiation basically has to be at the same temperature as the walls. And you get spectra like this, where it's redder the cooler it is, and it gets bluer the warmer it is. People have known about that for a long time, but the shape of the spectrum had to be measured with spectroscopy, and it didn't fit the classical theory. Well, Planck came up with an explanation that involved the idea that the walls could only be emitting and absorbing electromagnetic radiation in discrete packets of energy, and that then the packets of energy had energy proportional to their frequency or inversely proportional to their wavelength. And if he did the thermodynamics, the statistical mechanics calculation using that idea, he got the answer that the spectroscopists got. And so that was a very peculiar thing, but there's nothing in Maxwell's equations of electrodynamics that says that the energy should come in chunks. Is this some property of atoms? Is this something, what's going on here? Well, Einstein did a bunch of work on this, showing that you really had to, in order to understand it, you really had to assume that light was made of photons. But you also had to assume that light was made out of waves, because you saw interference phenomena. And in fact, you couldn't understand this long wavelength part of the Planck spectrum unless light was also made out of waves. So light is made out of particles, photons, and waves. We're getting into quantum mechanics now. Then along came Niels Bohr. And he had the idea that you could use the constant, Planck's constant in the black body formula, and that maybe that also quantized other things. And the first thing he tried was angular momentum. And he made a model where he put electrons in orbit around a nucleus and quantized the angular momentum according to Planck's constant. And he came up with something that had been known for a while, the hydrogen spectra, the visible hydrogen spectrum. This is the Bohrs series. There also is an ultraviolet series called the Lyman series, but this is Bohrs. And basically, by assuming that the emitted photon had an energy which was the difference between the energies of these orbits that he quantized. Now, this is peculiar. Your Rydberg atoms radiate at an energy which is very close to the energy in which the electrons would seem to be orbiting. But this frequency is different from the frequency of either this or this, but nevertheless, the theory worked. And it got the right answer for hydrogen. Now we get into a new spectroscopic invention. X-ray spectroscopy. A fellow named Moseley came up with the idea that he would use a crystal as a diffraction grating. And he knew that if he applied Bohr's theory to atoms with more highly charged nuclei, that the energies would go up and the energies of the emitted photons would go up. And he could predict based on Bohr's model what that would be. It's a bit naive to do that now that we know more quantum mechanics, but it actually worked pretty well. His model was that the atom only had one electron in it, which isn't what happened. It isn't the way it is at all. Nevertheless, if you looked only at the lines with the shortest wavelengths, they very nearly matched the Bohr theory of a single electron atom. And that became an objective measure of the atomic number, something that the chemists had never had before. they'd put the elements in series based on their atomic weights, and that usually worked, but not always. And there were gaps, and were the gaps real or what? And now with Moseley's technique, you can measure the atomic number, and you can say what atomic number every element has. And this was particularly important toward the end of the periodic table, because beyond lanthanum, nobody knew how to number the elements anymore, because they didn't know how many rare earths there should be. And Moseley figured that out. And then, just to show that extremely bright people can sometimes be really stupid, he went and volunteered for the British Army and got himself killed in Gallipoli. Tragic loss to the world. Well, now, you know, quantum mechanics is developing, and it's getting more sophisticated, and we start getting the idea that electrons are photons are both particles and waves, and de Broglie comes up with the idea that electrons are both particles and waves, and the whole thing gets, you get the Schrodinger equation, the whole thing gets much more sophisticated. And now that makes spectroscopy even more powerful, because you can use spectroscopy now to probe atomic structure. And one of the more interesting things about this is that you find there are these things called selection rules, where if with Bohr, basically, you know, any electron can drop from any level to any other level. But when you start understanding more about the quantum details, it's hard for an electron to change levels, except according to certain rules. So you see that these are the lines that are the allowed transitions. You can never have something go straight down. And I'm going to say, what? Never, hardly ever. But they always have to change orbital angular momentum by 1 unit. This is because the photon has a unit of angular momentum, and you have to conserve angular momentum. But it turns out that these are, and you see these in laboratory spectra, and you can use them to figure out which line is due to which levels, and you can figure out which levels, you can figure out whether this is a P level or a D level, if the upper level is a P level or a D level, and you do a whole bunch of things. You can really look into atoms and figure out their structure. But it isn't an absolute rule, and sometimes atoms can manage to do a trick. As one of my fellow students said when we were studying this as undergraduates, it can reach out to the side and throw a photon sidearm, and it can get another unit of angular momentum, and it can manage to make one of these forbidden transitions. And that turns out to be what nebulium really was. It's a forbidden, Bowen figured this out. He was studying the energy levels of ionized oxygen. And he found a forbidden transition, looking at a diagram like this, that matched, or a couple of forbidden transmission that matched the 2 lines of nebulium. What happens is in this gas, in this nebula, the gas is very diffuse. And so there are certain energy levels in ionized oxygen where if the atom gets in that energy level, there's no allowed transition that gets it out. So it just sits there. It just sits there. And in a laboratory flame spectrum or an arc spectrum, you got atoms banging around all the time. And what happens is that when they bang together, they knock each other into different states. And so the oxygen atom has a way to escape from this trap, and it doesn't emit this forbidden line. But in this very diffuse gas, the collision rate is negligible. And so eventually the oxygen atom goes and it reaches out to the side and it throws a photon and it makes a forbidden photon. And that's what nebulium was. So identifying new elements from spectra was a good trick, but it doesn't always work. And that's very typical of science. Okay. I'm going to jump forward quite a bit because we're now getting into areas where spectroscopy was constantly looking deeper and deeper into atoms and refining the quantum theory, and the quantum theory was getting refined, and there's more small effects that were predicted by the theory and confirmed by spectroscopy or observed in spectroscopy, and then somebody came up with a theory, and it got really complicated, and I don't have a year to talk about it, so I'm just going to skip over all that stuff and just say that spectroscopy was a tremendously good tool for probing what was going on inside atoms. And now we're going to talk about space some more. We already talked about nebulium and how that was kind of a misstep, but now let's talk about more positive things. Instead of using a prism or a grating, another way to measure spectra, to get spectra, is to take advantage of Planck's relationship between the frequency of a photon and its energy. And what you do is you catch a photon and you measure its energy. And for this image, the way we did it, and I will say we because every photon in this image came through the measurement chains that I designed. We captured the photons in a silicon chip, and each photon deposited its energy in the silicon chip, and about 1/3 of that energy went into electrons. And so you get a cloud of electrons, maybe, typically 1,000 for an X-ray. And then you measure that charge using electrical circuitry. And so you've got the energy of that photon. And now you can make a spectrum. And this is Cassiopeia A, which is supernova remnant. And it's got a bunch of stuff in it. And here, these lower images are where the data analysts have separated out the photons that are in the silicon line, the photons that are in the sulfur line, the photons that are in the calcium line, the photons that are in the iron line. And then these things are actually coming from free electrons in the shock wave that surrounds this supernova remnant. So they're not from atoms at all. Now you can talk about the composition. You can look at the line widths and say something about the temperature. You can look at the line shifts, say something about how fast things are moving, and you can really peer into this flat object and understand a great deal about its three-dimensional structure, although you can't understand everything, unfortunately. So this is a really good way of doing astronomical spectra, doing X-ray spectrum in particular. One huge advantage over a classical spectroscope is that you don't need a slit. And the problem with putting a slit across this thing is then you get very few photons and you don't learn very much. But with the non-dispersive spectrometer, you don't need to restrict where the photons are coming from. So you can take a full up image of the object that you're looking at, and then you can dissect it in terms of it's in terms of the lines that you're seeing. I go back a few pages here, and this is another non-dispersive spectrum. This is of a cluster of galaxies, the Perseus cluster. And this uses a much more difficult but much more precise form of non-dispersive spectroscopy. The trouble with doing it with silicon the way that I'm an expert at is that I said that about 1/3 of the energy goes into electrons. Well, 2/3 of the energy goes into heat, but that is a statistical process. And sometimes it's a bit more into electrons and less into heat. And sometimes it's a bit less and a bit more. And that limits your spectral resolution. This is the only spectrum ever made from a quantum calorimeter in orbit. Because right after they made this, Ops broke the satellite into 11 pieces. Don't laugh.
Oh no.
One of the most catastrophic blunders I've ever been connected to. I had nothing to do with the blunder itself, but I was working on this mission. I didn't do the quantum calorimeter. I was actually working on another silicon non-dispersive spectrometer on the same mission.
Well, did they at least replace it?
They're rebuilding it.
Yeah.
They're rebuilding it. I'm upset because it wrecked all my business with Japan, because this is a Japanese mission, because they're rebuilding it from the prints that I sent them, and they don't need my help anymore. And, you know, my Japanese colleagues and I had all sorts of plans for follow-ons and better things and all that, but all the money's going into the rebuild, and so I'm completely uninvolved with the Japanese space program now, which is one of the annoying things in my life. But U.S. space program is doing some pretty cool stuff too, so I can't be too upset. Anyway, this is a much more precise way of doing the non-dispersive spectroscopy, because what this does is it uses what's called a quantum calorimeter. It actually, instead of taking the energy from the photon and turning some of it into energy of electrons and turning some of it into heat, it turns all of that energy into heat, and then it measures the temperature of the detector, the jump in the temperature of the detector. And because it turns all the energy into heat, this statistical division doesn't happen. And so you get all the energy. And if you have a good enough thermometer, which is extremely challenging, this thing has to be cooled to 50 millikelvin. And it's a huge thing with layers of liquid helium and adiabatic demagnetization refrigerators and all this stuff. Very hard way to make a living. I prefer the silicon, but it makes very precise spectra. But we're not going to see another one of these for a few years. Okay, so finally, there are lots of other spectroscopies. Light is only one of the things you can take spectra of. And here's a very different spectroscopy. This is asteroseismology, where you look, instead of spreading the spectrum of the light out, you just measure the quantity of the light and you look for pulsations of a star. So stars vibrate. And as they vibrate in, they ring like bells. And if you carefully measure the light coming from a star, you can see those vibrations in the intensity of the light. And now you use a computer rather than a diffraction grating to figure out the spectrum of those vibrations. And here's the spectrum, and there's all these lovely lines. And this is instead of the atomic energy level plots that used for atoms. This is the kind. I'm not going to explain this. This is the sort of plot that you use to figure out what all these lines are from, and from these you can probe the interior of a star. You can measure how big it is. You can measure how massive it is. You can tell how fast it's rotating. And you can really characterize a star from these peaks. And so another space mission I'm involved in is called TESS. And this, in fact, was created from TESS data. But what TESS is really intended for, although it's very good at this, is finding planets by the dips that they make when a planet comes between the star and you. It cuts off a little bit of the light, and the light from the star dips, and you see that, and that tells you that there's a planet there. But that's a tricky business, and it's hard to measure the light perfectly precisely, and there are other things that cause you to see dips and all that. And so a full up kind of exoplanet observation consists of finding a few dips, predicting an orbit from the dips, and then going and looking at that star with a very high resolution spectrograph. These things use two gratings. They use a coarse grating at high order, and they use a fine grating at low order, and they cross disperse the spectrum in 2 dimensions, and they get resolutions of 70,000 to 1, something like that. And they have to have extreme temperature control so the gratings don't change size as you're doing the measurement, and very careful calibration. But they can measure the Doppler shift. As the star moves toward you, it looks a little bluer, and it moves away from you, it looks a little redder. And they can measure the Doppler shift now to about 1 meter per second. A slow walk. And so the planet is orbiting around the star, but the truth is the star and the planet are orbiting around their mutual center of gravity. And so the star is moving back and forth as the planet moves around. And you can see that Doppler shift. And with that, you can confirm that these dips are actually due to a planet. And then you can dial in asteroseismology, and you can figure out what the mass of the star is and how big it is. And from the mass of the star and the Doppler shift, you can figure out what the mass of the planet is. And from the size of the star and how deep the dips are, you can figure out what the size of the planet is. And then if you really have, the right conditions, the right kind of star, bright enough, a big enough planet and all that, you can actually look at how the spectrum of the star changes as the planet goes in front of the star and the starlight shines through the atmosphere of the planet. And you can also look at the light, how it changes when the planet goes behind the star and the reflected light from the atmosphere disappears. And you can look in those spectra for lines, and you can figure out some things about the chemistry of the planets. So even though we find the planets with photometry, which is, not spectroscopy, it's mostly spectroscopy that we use to figure out what we're looking at. And with that, I'm done.
Oh, marvelous, marvelous. Thank you.
Yeah, that was really great. Thanks. Thanks so much, John.
A question. Of course, the laboratories that I work with, most of the stuff we work with is double beam, as we call it. And essentially, again, it says that one is reference and one is sample, and we're constantly looking back and forth, so that as things change over time, and there's all sorts of changes that can occur, both of them are going to have the same relative, and the only difference between them is going to be the sample. Now,
Yeah.
I've noticed that in yours,
We don't have that option. It's expensive. It's heavy. You can't always do it. How do you work out all those problems that you have with drift and noise and all that kind of stuff?
Well, a lot of ways. They actually do double beam with the high resolution spectroscopy, where they'll switch back and forth between the thing in the sky and a reference source. So yeah, that is something that you do. Now, for something like that Cas-A spectrum that I showed you, you really can't do that. But what you do have is the advantage that you have dark sky around it. And so you can look at what is going on, what seems to be going on in the dark sky, and you can use that to estimate what the background radiation is. And
Virtual double beam.
Virtual double beam. Yes, and sometimes we'll take a detector and we'll scan it across the object in the sky. So again, it's very much like double beam. The background is tricky.
I have. I also have a couple questions.
At low signal to noise ratios, I mean,
Oh yeah,
really difficult.
Yeah,
You're
Joe.
looking at something a gigaparsec away. I mean, with Chandra, we're sometimes looking at 1 photon per 1,000 seconds.
Talk about signal to noise.
Joanne's question made me think of one. We hear a lot about the cosmic microwave background, and microwave is just another frequency of light. Does anybody look at the spectrum of the CMB to see if there's any emission or absorption? And
Absolutely.
yeah.
First of all, my old friend and colleague and mentor Ray Weiss had a space mission called Kobe. He's much more famous for getting the Nobel for gravitational waves, but he had a spacecraft called Kobe that very carefully measured the spectrum of the cosmic background radiation and found that it is extremely Planckian. It fits a Planck spectrum extremely well. Now, I'm not aware of using it as a background for getting absorption lines. For one thing, it's very hard to find things in the universe. It's not impossible, but it's very hard to find things in the universe that are colder than the microwave background, which means that, as Foucault figured out, when you're going to see lines, you're going to see emission lines on top of it, not absorption lines. So it is used for estimating the Hubble constant. It's not a great way to estimate the Hubble constant, but what you can do is you can find yourself a cluster of galaxies, and then you take an X-ray telescope and you measure the spectrum of the gas in the cluster of galaxies, and then you measure the cosmic microwave background in that direction, the cosmic microwave background that's coming through the cluster. You really don't use spectroscopy for that, though. You're just measuring how much. You're not really trying to look at a spectrum. Okay. And what happens is that the hot electrons in the cluster gas scatter some of the cosmic microwave background photons out of the cluster. And so at microwave frequencies, at X-ray frequencies, the cluster looks like it's at millions of degrees, and at microwave frequencies, it looks like it's a little colder than the actual cosmic microwave background, because these photons, the electrons have scattered the microwave photons out of the line of sight.
Cool.
But yeah, it's not. Yeah. It's not a great illuminator because it's Planckian and thermal and it's everywhere.
And it's cold and weak.
And
yeah.
Yeah.
I had another question about TESS. You talked about TESS and astroseismography, measuring the vibrations of stars and whatnot. That seems like it would be really hard to do with stars because they're so far away. How can you measure the vibration of a point of light? Is there just a subset of close stars that are amenable to that?
No, it works better on close stars, but we are designed to look at close stars. TESS, the juiciest exoplanets are the ones that are closest. So, it corresponds quite well. The answer is when you hit a bell, cover one ear and hit a bell, and you still hear the bell ring. Even though you're just listening with one point, essentially, you still hear the bell ringing. And we see the star ringing just from the whole light from the whole disk.
Okay.
It's the same way that you hear a bell ringing with one ear closed, basically. So
the whole star has a gross vibration, not
it has a gross vibration, there's some orders you can't see because they involve one side getting dark at the same time as the other side gets bright, and so you don't see those. But as the star rotates, those modes will often move into a state where you can see them, where from a different point of view, you can see those modes. And so that all goes into the analysis. It's an extremely sophisticated science. There are hundreds of people working on it, and I'm just amazed at what they're doing. And it's really cool that they're doing it with data that is taken by stuff that I developed, but it wasn't what I intended it to be used for, but it's cool that it can do it.
That is awesome.
Photons and electrons, you can do this. It's cool. They're just there.
Yeah, well, each TESS camera has 4,500 electronic components in it.
You say each camera. How many cameras are
There are
there?
4. And I selected every one of those 4,500 electronic components.
You had to find capacitors with low tolerances and whatnot.
All kinds of stuff.
That's why you get the big
Low
bucks.
tolerances is low drift. Because I don't care too much about what it says on the capacitor as long as it doesn't change.
Wow.
Calibrate.
As long as you can calibrate, you're fine.
Yep. And for what TESS does, I've worked on absolute calibration, but for what TESS does, mostly what you need is relative calibration, because you're interested in how much the star dims, or how much the star dims as the planet as a ratio as the planet goes in front of it. These asteroseismologists are interested in how much the star brightens and dims as a ratio to its average brightness. And so a lot of the gross calibration stuff is automatic just in the data analysis. It's still very hard. The noise floor, these guys have the noise floor down to 10 parts per million, which is
Different from the infrared. What's a few percent between friends?
yeah.
I had another question. What about the James Webb Telescope? What will that be able to do for you and other scientists interested in this sort of technology that you can't do yet?
Well, it's a much better infrared spectroscope platform, infrared spectroscopy platform than anything that's ever flown. And of course, we working on TESS are excited about it because it will really, it should really revolutionize this atmospheric study stuff, where it can look at the starlight shining through exoplanet atmospheres or reflected from exoplanet atmospheres, and do it more precisely, do it on fainter objects, you just do a much better job than what we're able to do right now.
And then also, you know, supernova remnants and planetary nebula and things like that, where you have heated gas. I assume there's an infrared component of those that can be picked out.
Yeah. Not my specialty. I don't know how much you can learn from in the infrared about those things. Of course, the other thing is that it will do a lot of stuff on very distant galaxies where the we use to look at stars, we still look at Fraunhofer lines, but if you look at a distant galaxy, the Fraunhofer lines are in the infrared. And you learn about stellar populations by looking at, you know, the balance of the lines and things like that. You usually can't, for a very distant galaxy, isolate a single star, but you can learn about populations. And redshifts, of course, are very important. And again, the farther out you look, the more you have to do in the infrared. So it would be very good at looking at very distant things.
Oh yeah, really far away things. Yeah. Been redshifted. And then I've got a simple question for you. Why do so many of these devices use diffraction gratings instead of glass prisms?
Well, because a grating, you can make so many different kinds of gratings. You can curve them so that they do their own focusing. You can blaze them so that they favor certain angles. You can have reflection gratings, you can have transmission gratings, and then you can control the grating spacing to match whatever you're trying to do. Glass only has a very limited number of compositions, and so you're limited in what you can do with glass. Now, yes, we use glass prisms sometimes. Some of the two-dimensional spectroscopes that use coarse gratings at high order do this cross dispersion to do the order separation with glass prisms. So that works. I mean, the other problem with glass is that if you rule a grating with a particular pitch, say a 10 micron pitch or something like that, well, you can use metrology methods and say, okay, my grating has a 10 micron pitch and I know what it is, and that's that. The trouble with glass is that you have to calibrate it, and it changes with temperature, and different batch of glass will be different and all that. So glass just isn't suitable for the most precise, and if you have a 10 micron grating, then you know the angles for a given wavelength. It's just math.
Yeah.
Whereas also glass, you have to know its optical properties, which again depend on fine details of its composition, which are difficult to measure. And glass is trickier stuff to work with than a grating.
Yeah, and also, it's limited in its transmission properties. It has a cutoff on both ends.
That's right.
Whereas a grating has a very, very wide range. And and again, when we deal with first order,
gratings and X-rays,
it goes all the way with the same grating. So that's one of the cool things. You can the same grating that you use in one end of the spectrum, you can use it at the other end of the spectrum. Just looking at different orders, and that's fine. You can do that.
Yeah, as long as you're careful not to get confused by what order you're looking at, it's great.
And
it's not that hard.
One of the things you can do is you can filter it out. You can actually have filters in there that say, well, I'm going to eliminate these orders. I'm going to eliminate these orders. So the only ones I'm going to allow pass at this time is these 1 or 2 orders. And then you can actually pull them in and take them out and say, well, now I'm going to look at this group and I'm going to take out these orders. Now I'm going to look at this group and take out these orders. And so you've got a really cool tool there in a grating that you don't have in a prism.
Well, thank you both. That's an excellent answer. I appreciate that bit of enlightenment about analyzing spectrums. Right. John, as an astrophysicist, I want to ask you about a particularly famous spectral line called the 21 centimeter line.
Okay.
Do you have any, I won't ask you any leading questions, but does that bring to mind anything interesting about astronomy and astrophysics?
Well, it is a line of atomic hydrogen. It's one of those. It's what's called a hyperfine transition. It's not something that shows up in the Bohr model, that's for sure. It's one of those fine details of atomic structure is capable of producing that line at extremely long wavelength. And it comes from atomic hydrogen, which is all over the place. And it's very narrow naturally. In fact, it's a candidate to use as a clock. People have used hydrogen masers to make clocks that are better than the cesium clocks that are the official standard of time, and they use that line. And so you can use it to measure velocities either toward us or away from us extremely accurately. And from that, you can look at rotation of galaxies, and you can look at how things are moving around in hydrogen clouds. And it's a serious tool of probing structure, particularly the structure of our own galaxy and nearby galaxies.
Excellent, thank you. Well, we're reaching the end of our allocated time. We have about a minute left. Joanne, did you have any further questions, or shall we wrap up?
I'm good. I listened to the expert. Again, my field is the instrument is already built, and I use it. Whereas, and of course, you have to understand it. Whereas he builds the dang thing, you go, yay!
Well, the funny thing is, I don't usually build dispersive spectroscopes, although I do appreciate the folks who do.
And again, ours were all gratings. Again, my big ones, but we use two different gratings, one in the first order and the second order, and the second one in the first order, second order only. So yeah, and filters, and oh, it was great.
Well, great. This was a great program and an excellent follow-up to Joanne's topic about light and how we can use light to gather information about the universe around us. John, the technical details that you shared, I think, should be accessible to our viewers and informative, and it was really an excellent exposition about the way that we use spectroscopy and the way some spectrometers are built. So thank you very much. Thank you for everybody for tuning in, and thank you to the board or the panel members who could join us today. Ivan and Mike Albro. Ivan had some technical difficulties with his local internet, and Mike Albro is in, was it Florence, Italy?
The poor baby, he's in Florence. Oh, the poor guy is stuck out there and just
in the sticks, in the boonies.
The other physicists weren't here. I got to say whatever I wanted.
Right. All right. Well, thank you all, and we'll be back again. We're going to be back in 3 weeks instead of 2 weeks because I run the electronics and the YouTube program. I won't be available in 2 weeks, but hopefully our panelists will all be able to join us on the 24th of October, where we will be back with another Sidewalk Science. Bye, everybody.
Bye, guys. Have a great one.